Section 3.5 is all about ways of combining functions. We'll start with combining functions arithmetically, just regular addition, subtraction, multiplication, and division. Here's an example where f of x is 3x plus 1 and g of x is x minus 1. We'll start with addition. To add two functions together, you just add the singular terms together. So 3x plus 1 plus x minus 1 simplifies to 4x. Right, for subtraction, do the same thing, except we're going to be subtracting the two functions. 3x plus 1 minus x minus 1. The only thing that's different on this one is that the subtraction symbol distributes itself to both parts. So you'll actually be subtracting x and adding another 1. This will combine to 2x plus 2. For multiplication, we'll take both of the terms and multiply them. 3x plus 1 times x minus 1. This will require multiplication or FOIL. So I'll have 4 different terms to distribute. First, outside, inside, and last. You should simplify as much as possible. So for this one, we'll leave it as 3x squared minus 2x minus 1. For the last one, for division, it's just a matter of putting f of x in the numerator and g of x in the denominator. So another way to write this is f of x on top and g of x on the bottom. This is equivalent to 3x plus 1 divided by x minus 1. There's really nothing else to do, no more further simplification that can be done. So for combining functions arithmetically, just simplify the terms. There is one new type of operation that we haven't done yet. Only functions have what's called composition. They use an open circle to notate composition. Here's the definition of it. When you see an open circle, in practice, we should change it to read f of g of x. So f open circle g will convert to f of g of x. The textbook will interchangeably put these in. Sometimes they'll automatically use this notation, other times they'll start with the open circle. So you should recognize both of them. Okay, let's look at an example of that. For this one, f of x is x squared, and g of x is 3x plus 1. So we have to find f open circle g of negative 2. So the first thing I did here was went ahead and converted it to a more practical notation, f of g of negative 2. This is all about substitution. We're going to do the innermost part first. So this equals f of whatever g of negative 2 equals. All right, g of negative 2. I can substitute negative 2 into the value to get negative 6 plus 1, or negative 5. So that means I'm really finding f of negative 5, working from the innermost parts first. To finish this then, I need to go ahead and figure out exactly what f of negative 5 equals. So I'll do some more work down here. Now f of negative 5 will be negative 5 squared, or 25. Okay, working our way from the innermost parts outwards. In the next example, I have the same thing, except the order is different. It's g open circle f. This is actually going to be a different answer most of the time. composition of functions is not commutative. So I'm going to start this time with f of negative 2 because it's in the inside. All right. F of negative 2. Substituting negative 2 into the f function above, I get negative 2 squared, or 4. That number now gets substituted into the problem. We're trying to find now g of 4. So really what's happening is you're taking the answer from the inside part and making it the input of the outside part. To finish it, g of 4 is 3 times 4 plus 1, or 13. This is composition of functions. It's a substitution into the innermost part and then substitute it in to get the outer part. Another composition can be written is without a numerical value at all, when they just use plain x. Letter C is just read f of g of x. So I still need to do the same thing. I work towards the innermost part, which is g of x. But this time, instead of getting numerical value for g of x, it'll be the entire g of x function itself, which is 3x plus 1. What this is telling you to do is everywhere you see an x in the original f function, it now needs to be replaced by 3x plus 1. So what used to be plain x up there is now 3x plus 1 squared. It's one function substituted into another. You can simplify this if you want. You'll have to check the answers in the back of the book to see how far you're supposed to go. This is good enough for me, but if you'd like to write it out and to FOIL it, you can do that. This one would be 9x squared plus 6x plus 1 as an alternative. The second one is just the reverse, g of f of x, where f of x is in the innermost part, so that's what we have to start with. I'm going to substitute whatever f of x equals inside the parentheses. That would be x squared. Everywhere you see an x in the g of x function, it's now going to be replaced by x squared. So I'll have 3 times x squared plus 1. Totally different answer. All that's different is it's commutative, but you can see the answers are very different. One less type of problem that you'll be asked to do is like number 17. So what I did is I came up with an example problem just to show you how this works. The example I'm using refers to the graphs that are on number 17, on page 217. I said to find h of f of 2. So I'm going to start with f of 2. There's no function to substitute this into, so instead we're going to use its basic notation. F of 2 is referring to the corresponding y-coordinate when x equals 2 on the f graph. That's the dot that you see right here. Its y-coordinate is -1. So it's replaced with its function value. To finish this, I'm going to find out what h of -1 equals. So again, this is looking for the corresponding y-coordinate to x equals -1 on the h graph. That dot is right here. It's at 3. So there's no equations that are used, just the graph themselves, and the corresponding y coordinates that go along with each. I'm going to start from the inside and work to the outside.